Hello, guys. I think we can get started. Today, we're going to talk about Phoenix AI. No, I did not get a new job. We went through a rebrand last month. And today, we're going to talk about um, building Phoenix AI, what we've already built, and our roadmap, and what is the kind of database that agentic analytics need. I am Sida Shen. I am a product manager at Phoenix AI. And welcome everyone. Now let's get started. CelerData is now Phoenix AI. It is the same team, a new name, with one new focus: building the analytical database for AI agents. And today I'm very excited to also announce our 80 million USD Series B funding to support the agentic era analytical database. This effort. Phoenix AI, formerly CelerData, is proven at scale. It's the engine, the database, the real-time analytical database behind petabyte scale production, by global leading enterprises such as Coinbase, Pinterest, Celonis, Expedia, and more. All right. It runs a cloud service (PLC) from day one, so data stay in your public cloud account and never leaves your account. And okay, so this is what we're kind of gonna cover. So first, we're gonna talk about the shift and why AI agent change the requirement for the underlying infrastructure, the underlying analytical data and serving layer. And second, we're gonna talk about how today's data stack infrastructure for OLAP runs out of room, when the user is AI agents. And third, we're going to talk about Phoenix AI Cloud, what is available today, what does the database do, and who runs in production, some use case, some user stories. And then we're going to take a look at the roadmap. We're going to take a look at how we're building the one database for the full agentic loop. And then we're going to have, of course, time for Q&A like usual. First, the query consumer changed. But the analytical layer hasn't. Just a year, 2 years back, it's still like human writing SQLs, writing dashboards, and all of the query patterns are predictable. And the bottlenecks were always the human, that makes a decision. So we're pretty tolerant in terms of like how fast a query returns, right? And the result is always reviewed by analysts, by some people, some human in the loop. So accuracy and was not that big of a deal, so like real time analytics, having the most up to date data was not that important, right? And also human have memory, right? They know how to write good SQL. They know where the tables are, they know where the columns are, they know how what the database is, and they know like how each metrics are are persisted, are defined, either in their memory or in some kind of documents, buried inside of their Google Doc, right? But in the agentic era, when LLM generates SQL, it is a very different kind of workload. First, it's very unpredictable. I say 80% here, but to be honest, 100% of the query that agents write are unpredictable and inoptimized. And also, LLMs make decision way faster than human. It's not the bottleneck anymore. So latency suddenly become a lot more of a requirement we hear from the field. And also, agents, they don't know what's right or wrong. They don't have memory, right? So they don't review before they take an action. So having the most up-to-date data, having the most accurate result becomes that much more important. And also, there are no memory between sessions. Agents just don't remember anything, right? They don't know how you calculate, let's say, revenue for the last quarter, right? How do you do segmentation? They don't know, right? So it's a very different kind of workload. But the analytical serving layer and the database layer hasn't changed. Infrastructure is a very slow moving piece of technology, and that's normal, right? But the analytical layer does need a change today to satisfy, those requirements from AI agents. And to dig in a little bit about more about the concurrency, right? and one prompt can generate dozens of queries, not just one, right? Let's say a user asks, why did the revenue in Nevada drop 12% last week? And the LLM agent is going to decompose, understand the natural language, understand the question, plan, generate some sort of SQL, and start iterating, right? Start to do exploration inside of the database that generally spawns tens of queries per agent section, and they expect query latency to be roughly second level or under a second because the queries they don't just run in parallel, right? They do compound over time, and we also see a huge jump in terms of concurrency and QPS, typically 10 times what the users are asking for this year uh, compared to last year, right? And there are zero human review before the action, so the data needs to be the most up to date and the most correct and accurate. So this boils down to four real requirements for the engine or for the database layer. First is sub-second, not just sub-second on any query, on a polling query, right? A sub-second on ad hoc SQL, including a query that no one has run before, right? There's no computation built for that. And also unify, right? Agent needs a unified view of your all of your data and AI asset within your organization, right? So you both want real time access to your data, which is streaming, and also you also want access to your historical data, and being able to query both of them at the same time using standard SQL and have the query result returned in second level or sub-second latency, right? And third is very novel, right? Every single LM query is ad hoc. They don't really follow any pre-computed rules, predefined rules, right? It's arbitrary. Generate SQL, nothing assumed in advance, and also extremely inoptimized. And fourth is it has to be governed, right? Because agents they don't know what's right or wrong, right? LMs they don't know what's right or wrong, and also we need even more fine-grained access for those agents, so they don't access the information and make publish the information they should not have. And also we need audits for the agents. We need trace, right, to know exactly what they did, and optimize and secure, right? So that's the requirements. And today's stack, each one of the tiers run our room very differently, right? I basically categorize, what we have available in the market today into three bigger categories. So first is your real-time OLAP databases, right? Think of something like ClickHouse or Imply. And second, say is cloud data warehouse. Think of something like Snowflake, Redshift, BigQuery, Databricks. And then is the query engines, right? Think of AWS Athena. Think of your open source Spark or any managed Spark service, or Trino and Trino's variant, right? And they all run out of room for the agent requirements differently, right? So for real-time OLAP database, they're mostly built for single table, low cardinality, append-only kind of workloads. So it's really good for time series, for observability, right? So for the things that uh, that you can predefine, that is predefined, you can pre-compute, right? And where it hits a wall with AI agents is that they typically are not optimized to run join queries. They're not designed into the database, right? So you would need to pre-compute everything, make to do denormalization for all of your normalized tables, right? Which you just cannot do with agents query ad hoc 100%, right? And also it also comes with incomplete SQL dialects, not supporting join, not supporting subqueries. That can be another problem for LLMs because that's a limiting factor they need to consider, right? They don't have as much freedom, when the SQL dialect doesn't support, what they want to do, and also weak data lake integrations, right? So these are real time, append only kind of real time, no updates or deletes, real time. But the big problem is they typically do not have a strong integration with your historical data layer, right? Your Apache Iceberg tables. Some of them do, but it's very difficult to run sub-second or second level SQL, on top of that with the real-time OLAP databases that are available today. And Cloud Data Warehouse, they are mostly built for scheduled BI, for batch analytics, for very complex SQLs that runs pretty quickly, right? But they're not really tuned for concurrency, right? So think of some kind of search workload, right? Or some kind of point queries. It's very difficult to scale that even to the hundreds of QPS, right? And also a lot of them have a really big overhead in terms of running a query, in terms of planning a query, for example, like Redshift, right? It always have like a multi-seconds latency floor. So if you want to optimize your query latency below like multi-second, it gets really, really expensive with most of these solutions, right? And also data freshness is not really what they focus on, right? They all rely on merge on read, right? So minute level data freshness is okay, live off of S3, but you want to go like second level, 5 second, 10 second, it will be very very challenging, or even possible with most of the cloud warehouses available today. And for query engine, this is just a large variety of them available on the market, right? But most of them, actually all of them, are not really tuned for low latency, high concurrency kind of workloads, right? Some of them are for more for ETL. Some of them are more for just in general exploration, ad hoc kind of use cases, right? Their latency are mostly in the tens of seconds into tens of minutes, right? They're built for a few big jobs, not really high QPS, low latency kind of jobs, right? And their freshness basically depends on Apache Iceberg or Delta. They probably have the best kind of freshness right now, but it's not really enough, for these kind of agentic workloads. And also, I want to double click on precomputation, right? A lot of the engines, a lot of the database vendors, they push an idea of denormalization, right? So you build a wide flat table in the beginning off of your already normalized tables, right? So you don't have to recompute the join on the fly. So the query runs fast. Yes, it runs really fast, but it comes with a lot of different kind of problems, right? First, the big flat table is a drawing of all of your tables, right? It's very, very wide. Typically, we see in production, it typically 10x your storage, and also it frees your columns. It becomes very difficult to do a schema evolution with denormalization in place. Just think of you want to change one column on your dimension table, but with denormalization in place, you have to like do the entire uh, pre-computed table as well with number of rows equals to your fact tables, right? That's data backfilling. That's very very expensive, and doing schema change becomes very very difficult. And also, it's a pipeline. It's the pre-computation pipeline, right? If it's not real time, you can use something like Spark. It's manageable. For depends on how many tables you have, but if it's real time, it's very difficult because join is inherently a stateful process, right? So you need to tap your toe into stream processing, and managing that for all of the tables is just not feasible for most of the team that we speak to. And on top of that, it doesn't really work, with agents. You cannot really pre-build the right white table for a query that you don't know what the agent's gonna run, right? If you run everything off of a flat table, off of flat tables and pre-aggregated denormalized tables, you're basically limiting the LLM's ability to do exploration, right? To be creative. So that's not good for pre-computation. It's not good for AI agents, and that's and that's why we built Phoenix AI, right? That is the one analytical database for AI applications and agents. So it answer questions, answer analytical queries at agent speed. It fits into your existing technology stack, simplifies your data architecture, and then it provides you with governed enterprise access. We're going to dive into each one of them one by one in the next few slides. So first, let's talk about the architecture, right? So first, you have the application layer on top, right? So you can run agents, you can run your customer-facing dashboards, applications, analytics, and then you have your internal BI tools, and then you have your other, in-product analytics. You have your enterprise applications, right? And these applications speak to Phoenix AI through Inside SQL, right? Through standard SQL or MySQL through the MySQL wire protocol, right? So your application still can stay the same, right? And this is the Phoenix AI core, and that's what really differentiates Phoenix AI. So it has a vectorized, massively parallel processing engine that is able to not only horizontally scale your your aggregated queries, but also you can um, horizontally scale your joins as well, right? A small join big or big table join big table, we're able to shuffle the data within memory, so it scales horizontally linear, right? It has a cost-based optimizer. It's very important for running joins with good performance, right? And also it features multi-warehouse isolation, physically isolated warehouse for your different kind of workloads, so they don't really affect each other. You want to make sure that your largest tenant or your most important workload gets the appropriate amount of resources all the time, right? And on the storage side, it's managed Phoenix AI table format and your Lakehouse in place, right? So let's dive into each one of them one by one. So your Lakehouse is your self-managed Apache Iceberg or Delta Lake tables, right? Phoenix AI is very optimized to read those data directly off of your S3 storage in those open formats and return the results in second level or sub-second kind of latency, right? It has a built-in cache, so anything off of S3, we minimize the communication, with S3 to achieve that. And if Apache Iceberg or Delta Lakes data freshness is not really enough for your use case, you can also have those data. For example, your Kafka topics, or you have a transactional database and you want to analyze those data in real time. You can CDC the data in to Phoenix AI's own managed storage format. And then there you can do second level upserts and deletes in real time, right? And everything's governed by the same SQL layer, so you can join or union between the two, right? So it's one unified SQL layer that sits on top of all of your real time, the managed ones, and your historical or quasi real time data that lives in your data lake, your data lake house, right? And everything persists off of S3 or S3 compatible object storage, depends on what you run on, right? Both for the internal table format and your lakehouse format in your VPC. And talk about in your VPC, the whole entire cloud service is BYOC, so everything runs off of your AWS account, and data stays within your parameter. And also we have encryption that makes sure that we don't see the data in any way. So this is the architecture of Phoenix AI and how to run agent SQL fast. The really core of that is cost-based optimizer, right? And that's really a two-part question, right? So how do you run join queries quick? That's the planning part, right? The planning is a very, very difficult, challenging problem to do, right? And the state-of-the-art approach is a cost-based approach. Basically means that we collect statistics periodically from your real data in real time. For us, it's every 10 minutes, but also configurable. and and a lot of column statistics, right? And using those statistics to derive the best drawing order, the best distributed drawing strategy, the best drawing algorithm to use, right? And all of the data pruning we can do in along the process, right? So that is the best, the probably the only viable way of running joins on the fly in a distributed way, right? And another part of having a good optimizer in the agentic world is that agents, they don't have memory. They don't really know which table is big. They don't have the statistics, right? And before it's the human that writes the SQL, that knows the data, right? That optimizes the SQL, but with no human in the loop, like what can we do, right? And you cannot really have the agent collect the statistics and do that part of the job because we collected, we know how big that is. It's definitely too big for the very precious context window that LLMs have today, and also really distract them from like their actual job, right? So having a cost-based optimizer is not only uh, like a joint performance problem anymore, right? It's even more important. It's a must-have. When you have agent writing the SQL, even that's not a joint SQL, you still need very optimized SQL written if you don't have a good optimizer, right? So we need database to do the database job, which is give it any SQL and return the result in a in good performance with good latency. And this is the upside problem, right? So real time, there are many databases in the market today that is able to perform real time ingestion, right? Less than 5 seconds, less than 10 seconds is really not that uncommon in the industry today. But the real problem is, what if the data changes, right? What is it's not just a log from your website, or is some kind of observability kind of like workloads? What if your data changes? And that could becomes a much harder problem with columnar storage, right? Most solutions uh, depends on merge on read. Basically, it has a compaction job in the backend. Try to merge all of the different versions that the writer writes in the background is never fast enough. So in the end, it affects query performance a lot. For example, for ClickHouse, if you scale your data freshness into, let's say, under a minute for most of the cases, depends on your use case and your hardware. It will affect your query performance with upserts and deletes. And this is exactly why we built our primary key table, right? It has a row level index that maps from the hash of your primary key to wherever that's stored in the storage. So we're able to complete the upsert process, the delete process in O1 time complexity, right? So we're able to do all of the updates and deletes without ever impacting query performance. And though also the index and the table, the data and the index, they all persist on S3, and we load them into memory on demand, right? So not really the merge on read overhead anymore, right? So you can have less than 5 second ingest to queryable, including updates and deletes without impacting your query performance. And that's streaming upserts, that's real-time upserts, real-time data freshness. And then it's the governance part, right? And we already built everything inside of the database, right? So for access control, we're RBAC, role-based access control, with column and row masking policies. So cell level policies, in terms of which row can access which data, right? And we keep a complete audit trail for all of the queries, all of the operations that's been done inside of the database, right? So leave room for us to create audit trailing, for AI agents, and also everything's BYOC. So PhoenixAI do not have access to your data. It's encrypted and stored in your own AWS Azure or GCP account with your private networking, and the data never leaves your VPC, right? And it's available on all three public clouds. And how it compares, to the other categories I just talked about, in terms of different requirements from AI agents, right? So first is full ANSI SQL, right? It's a dialect that AI agents already know, right? It can run sub-second on normalized tables without precomputation, so your AI agents can do free exploration, run any SQL that it wants, any crazy inoptimized wrong SQL at that inoptimized SQL that it writes, we return the result in second or sub-second level, right? And concurrency, if it's an easy kind of point query, we can easily scale that up to 10,000 QPS or a easy aggregated query, we're able to scale concurrency to a crazy level. We don't really have that kind of per query overhead that a lot of the cloud data warehouses and query engine have. And latency, sub-second on ad hoc SQL, and freshness and historical data, right? So we're able to provide you with sub 5-second data freshness and also a unified SQL layer for your real-time data that's stored in our format and the data that you bring yourself. It's a BYOI, bring your iceberg. Just made that up. Yeah, your iceberg table and your real-time data that's being served inside of persist inside of Phoenix AI, right? So a unified SQL layer for all of your data AI assets. So who runs Phoenix AI in production today? We're gonna take a deeper look at two production stories and more. So first example is Conductor. They are a search optimization and content intelligence firm engine platform that you can use to optimize your presence inside of the web, inside of search engines, and also inside of AI, right? So have ChatGPT, like recommend your category and whether your product is the first on the list. Those kind of optimization, right? And they were building answer agents for their customers, Zoom and City, in ChatGPT and Claude. Basically, I want to ask like how optimized is my these keywords right now, and then it returns the data, right? So and it's already running in production. For a query that scans 240 million rows, that is able to return in sub-second um, latency with their customer facing concurrency, right? And also everything is ran with zero precomputation. So because agent is running the SQL, right, it is ad hoc by default. And also from idea to production because of not needing to move all of the data from their lakehouse and also not having to build all of the denormalization pre-processing pipelines from having an idea to design to implementation to POC to production. The whole thing took less than 2 months. And we have a 30-minute demo with them with our last webinar. We can share the link to you later. And the second example is a Demandbase. Demandbase is a B2B go-to-market platform, right? So basically, you have, as a marketing team, right, you have leads that come in, right? So what they do is they evaluate the intent of each one of your leads and which one is ready to buy, right? Then that is with a lot of machine learning powered um, uh, metrics and also very complex logic, and also that is customer facing in nature because that's built into their product. And they run everything. They used to run everything off of ClickHouse, and because of the complexity and the number of table that they had, they were forced into denormalization and basically 10x their storage. And after they move to CelerData, now Phoenix AI, they're able to reduce their storage capacity by 90% by eliminating 100% of the denormalization pipeline. And also they were able to consolidate all of the 49 ClickHouse clusters into one Phoenix AI cluster that serve petabytes of normalized data that persist in Apache Iceberg, right? And this right now serve both of their customer facing in product analytics and also demand-based AI, right? And both are running in production and scaling today. And also we have more use cases that are in production. So first is Yuno, right? Customer facing payment agent. They migrated from a cloud data warehouse and scaled their freshness from like 1 hour to 5 seconds with upserts and deletes. And they built a LM power agents on top of that. And second is Celonis. Celonis is a process mining platform that really have some of the most complex queries and logic I've ever seen in my life. And some of the results they got. So for a query that's 20 billion rows scanned, they run at this kind of scale, And the biggest query they write is with the 100 table join in a single query, which is just insane. And Coinbase, they run blockchain analytics, customer facing to on PhoenixAI on tables that reach more than half a trillion rows, and they have 300 plus denormalized tables, normalized tables, not denormalized, normalized tables, and they run all of that in sub-second, serving query latency. It's a quote from Xinyu from Coinbase. Okay, so that is what we have today, right? The PhoenixAI real-time analytical database. And this is what we already built. And now I'm going to talk about the roadmap, what we're building, and what we are going to build in the future, right? So that's a database. But with the user shifting from human to AI, the connection needs to rebuild as well, not only the engine, right? The engine needs to be sub-second, needs to be ad hoc, needs to be everything. But without the right kind of connection, um, nothing really works, right? And agents have no memory between sessions, right? Different from human. Human has a brain, right? Agents, they don't. And they have no knowledge of your business logic because they don't have memory and because they can't really, talk to a human. And they don't really have access to all of the private notes that each one of your analysts have, in their back pocket. And it acts with no human reviewing it. It cannot review itself. If it could, it would have just written the right answer, right? So what we're building next is a connection layer, right? That bridge those gaps. A human, a SQL layer is enough because we know all of that. We have memory, but the SQL for agents is way more complex than just SQL. It needs a whole entire memory um, layer. It needs a whole entire guardrail and trace, and to make sure that they're doing the job you're asking it to do, right? So this is what we're building, and what's available today is the real-time analytical database that runs on all three public clouds available today, and then we're building the semantic layer, semantic SQL, and then we're building a context base and agent observability and agent governance same time. I'm gonna dive into each one of them a little bit today. So semantic SQL. So what's wrong with SQL? LM already knows SQL. It already writes pretty good SQL, but what's wrong with it, right? It's all comes down to, do you actually want your LLM to reason on columns and tables, or you wanted to reason on attributes and metrics, right? So LMs are really good at natural language reasoning. Let's keep it that. Let's hide all of the database schemas and all of those underneath, right? So that's exactly what we're building. It's a extension of SQL, semantic view and semantic SQL, right? That enable your AI agents to directly um, reason with only natural language without ever touching the schema and everything, right? And also, we have a lot of checks at compile point, so we can make sure that everything that the agent is writing uh, is correct, or we can reject it at the compile layer. And also, this gives us a lot more room for performance optimization, given the semantic information, right? From one to another, we can prune a lot more things than before. And then the context base is a markdown native store. That's an extension of our already existing Phoenix AI storage format, right? For knowledge, for memory, for agent scale. And this serves two purposes. First is to support your semantic SQL, semantic layer, right? The memory and the scale and the search functionalities. And second, it can be your knowledge base for your excuse me, for your analytical your data, right? It can be the knowledge base for your analytical data. And then it's agent observability and agent governance. We already have the capability in our database layer that enable you to do cell level access control, right? You enable you to do role based access control, right? And we also already have all of the traits available. So this is just building the application layer, for that to be agent native, agent friendly. And this is the roadmap at a glance. Foundation is already in production, Phoenix AI Cloud. That is the analytical database. Customers are already deploying in production, running on petabytes of data. And then Q3 2026, we're gonna release the preview for agent native layer. So that's a semantic SQL and semantic view paired with context base. And then Q4 2026, we are going to release the preview for our trust and operation, guardrails and trace for your agents. And in the second half of 2026, we're going to release fully managed Phoenix AI and Phoenix AI Anywhere. Basically, it's on-prem version of Phoenix AI. That's it. Real-time analytics for AI agents. Answer at agentic speed. Fit into your existing technology stack. Simplifies your technology stack. Govern enterprise access. And start a free trial today at cloud.phoenixai.ai. And get a 30-day free trial. And any questions? All right. I think that's it for today. Thank you so much, guys, for tuning in. We're going to try to run these webinars twice every month going forward. So thank you so much for being a part of this. It was a lot of fun. Thank you so much. See you again next time. Thank you.